jointly conducted by Dassault Systems and Vias. Just to give a background, this is this is the we had the two prior webinars. The first was an overview of simulation and CPG. The second webinar was on rigid packaging simulation, and this is the number 3 seminar on flexible packaging simulation. We will follow it up by another seminar on the transportation theme. Uh, to give a very brief and a quick introduction about Vias, this will just take a couple of minutes. Who we are? We are a solution partner of Dassault Systems for the SIMULIA brand. So we have an in-house team of PhD and masters in fluid mechanics, solid mechanics, optimization, analytics, and have deep expertise in the SIMULIA portfolio, from Abacus, EyeSight, FESafe, Tosca, um, Dalmia, and Katia. Our experience spans across consumer goods, oil and gas, petrochemicals, um, and process industries. So we do provide support consulting services also. So I'll keep this brief here about the seminar. Um, so the way I would like to proceed is that for the first few minutes, I want to kind of briefly recap what the platform is about, what are the different products that we have. I'll keep this as brief as possible. Uh, I know that this is a bit of repetition from the last seminars, but for people who might be joining in for the first time, I just wanted to cover kind of a brief kind of an overview. So the first on the 3D experience platform, uh, the idea really behind the 3D experience platform is it provides an integrated, unified database for CAD, for your PLM, for your simulation, and also for managing your subsequent your processes. So you can start off actually with your initiative, not just from your CAD. What exactly is the initiative you're after? You can put a search whether a particular initiative for a product initiative has been launched in the past, and you can kind of copy that and modify that. So once you start, you have your digital assets. You start from a baseline of your digital assets. You go ahead and make your CAD model, uh, or you reuse those CAD models. And once you do that, you can also do your artwork and labeling inside the 3D experience platform. Uh, and the part we'll be focusing on is the perfect test, which is the simulation part, where you can define your multiple uh, all the scenarios that you would like to simulate, whether you want a top load, drop load, and so on. So before even actually making the product, if you want to test out how the product will actually function in real life, you can do that. So what this allows, I think, to the FE analysts who have been using this platform, or the Abacus solvers, this kind of they already know of it, but just to kind of uh, you know reiterate, you can explore the design iterations, much more design iterations than would be otherwise possible. You can reduce your time to market. You can actually and you can reduce your physical testing. So instead of doing physical testing for, say, maybe 10 of the product prototypes, you can focus on your two best ideas, and you can explore your design space in much more details. So we would focus specifically on the flexible packaging for today, uh, and kind of a brief overview of the Simulia product portfolio. So the Simulia product portfolio, so basically Simulia is a Dassault System brand which encapsulates all the simulation product that Dassault has. So the key product is the Abacus solver, which is a very powerful structural mechanics solver. I would say probably is the best in the world for any of the complex problems, and flexible packaging does fall in the domain of complex problems. So it's also multi-physics. We have capabilities for fluid, electromagnetics, and we are adding more of the multi-physics capability. More importantly, it has the framework that you can bring in your own custom physics and couple it with the solvers that we have. We also have a process integration tool which is built in inside the platform, which can allow you to link your disparate simulation processes into one whole, and it also allows to deploy those processes across the enterprise. So if you are a simulation expert if you're an FEA expert who has mastered the methodology of doing a particular simulation, and you want more people in the company, in the organization, to be using it, that there are inbuilt deployment tools which make the task really easy. And there is also the optimization tools available for decision support. So as I said, we can explore a number of ideas, and like the moment you want to explore a number of ideas, how do you streamline the number of ideas you want to explore? How do you iterate towards the best solution? And that kind of broadly falls under design of experiments, optimization, response surface, and all those techniques. We can also predict the life of the component with the FE safe product that we have. If you want your product to to successfully survive about 400 load cycles, 500 load cycles, whatever that number is, would it survive that? So it's just not one simulation, but multiple simulation. So it's a, so it's a pretty comprehensive suite of simulation products. I would say it's kind of complete in most respects. If you want more information on any of the products, I can go in much more detail. I mean, we can connect offline and we can go in much more detail about it. So having said that, again, a reiteration of my earlier slides, about what is unique to the consumer goods simulation, which makes it a challenge. Number one is the complexity of the materials. Like the simulation technology applied to automotive and aerospace, it's a very mature technology. People have been using it. There are teams using it, and part of the reason it's very easier to model steel, aluminum. Those follow much more. They follow laws which can be defined much more easily mathematically than if you have to model, say, paper. And we'll talk about paper in much more detail in this seminar. So well the so it's actually far more complex to model something like a paperboard container or a diaper than it is to model, uh, say, a car crash or an aluminum, because the complexity of the material models is much more difficult. What makes it unique is that you have material which deforms heavily, and so it's really at the edge of what can be solved by the conventional techniques. We have to kind of go into much more advanced techniques, and that's been the focus at Simulia, has been for the last 2 decades, that a number of these advanced techniques have evolved. And I think now is the time that more and more consumer companies are adopting it. A number of consumer companies have successfully adopted it, and we'll talk about some of this in the flexible packaging. We we can also solve. I mean, the solver needs to be able to solve complex physics. Often you require to take a first principles approach. And does the solver allow that flexibility? Often you may need to define your own user material or your own constitutive model for the material properties, or it might be physics, and you might need to couple that with with the existing solver. So it needs that framework. It needs to be able to handle highly nonlinear contact. The contact can really be very difficult because you can have the material folding onto itself, and all sorts of things happen. And and the stability of it. I mean, even if you solve a problem, how do you ensure that it's stable enough that others can reuse it? Those have its own kind of unique challenges. Having said that, this is the slide I love to show, just because on the left hand side you have a real physical test, on the right hand side you have a virtual test, and you can see this really how realistic this is, how realistic it looks. And I can tell you that to get this close, it's a challenge. And an abacus has been kind of tuned over a number of years, I would say decades, just to get this kind of answers more accurately. So that's kind of the brief kind of a recap about what this is about: the 3D experience platform, the Simulia product suite, and the consumer product, and the unique challenges for the consumer packaging industry. We would take a deeper dive into the flexible packaging world. So first we will talk about the paper-based containers, and then we'll talk about the pouch filling model, and at the end of it we would look into a demo for pouch filling. So first, talking about the paper-based containers. So what do we need? I mean, if you think of a paper material, that's very, very different from your usual aluminum or your steel material. It behaves differently in tension and in bending. So I mean, like, the properties do not port over perfectly. So you need kind of a different kind of a constitutive model to handle it, and you need, a number of things need to happen. So, but I mean, if you think of it from a holistically, from a high level perspective, what you need is, you need a product that has high bending stiffness when you're making a paper based container with as few fibers as possible to reduce the material cost. And you need to understand how different designs of your paper based containers will influence the box compression strength, and are you overutilizing the materials, or you need to be using less, or you can actually use less materials, or you're under designed. Those answers, it's much more easier to get those answers via simulation. So just to get into the detail, any cardboard material, it consists of a fibrous network, and due to the manufacturing process, they are more aligned in one direction, the machine direction of the paperboard machine. And so the material property is anisotropic. So we need the flexibility to define anisotropic material properties. We need we need the possibility to define plasticity. So once it deforms, if it does not recover, and we also need to have the framework to define damage. So if it damages, would it be able to recover? So these are the material models which are available inside of Abacus out of the box. And often we require much more advanced techniques, and for that you can use the user subroutine approach, which would allow to go after it. So to talking more of the paper-based containers on the folding of paperboard. So here we have four, of the plots which I have put together. So if you look, I mean, if you look at the first plot, the idea really, well, what I want to convey is that initially the bending stiffness is proportional to the force you apply. It is what you would expect. But the more the force you apply, the plies start to buckle, and also you have delamination happening. So, progressively, the buckling is going to make your bending stiffness lesser and lesser. And once you reach a certain point, it's basically your bending stiffness essentially is constant. Your material is kind of given way. So that's kind of the broad challenge, which needs to be handled. And here is kind of a scenario, which is a complete load cycle, loading and unloading. So you load it, there is a crease built up, so you can see the crease, and in the paper. So this was done using a paper user material model, which was built inside of Abaca, which was actually custom built. Uh, if you have interest, we can talk about it offline about the details about this. And just to proceed over here, so but you can accomplish a lot even while using the material models which are available inside of Abacus out of the box. And you can, what you need to define, you need to define your elasticity, you need to define the the material properties in each of the individual directions. You need to define plasticity, and and you need to define some kind of a failure law. So there is an elasticity curve, there is a plasticity curve, and the failure law, and you have the kind of the directional elasticity, which will allow you to define define the material properties along different directions, depending upon the way your fibers are aligned. So this is, like an example of the, okay. So once you do that for the paperboard, I mean for the paperboard containers, the two crucial tests are the compression test and the bending test. So this is an example of the bending test. You need to be able to model the corrugations, and and to optimize the number of layers. That's kind of something which can be explored virtually. Is just one corrugation layer enough? Do we need multiple corrugation layers, and so forth? So what we are trying at Dassault Systems, I mean, is that they want to kind of make it simpler and simpler to define most of the common workflows which are experienced in industry. So inside of the structural package design, there are some kind of CATIA apps which will allow you to build this workflow much more easily. So and the two crucial tests, as I mentioned, is the edge compression test or the box compression test. So that can be performed templatized to the 3D experience platform, and you can reuse those templates. You can take those results, and you can look for more homogeneous. You can look for you can try to simplify your model. So here we have a one wall layer, and on the left we have a two wall layer. So we can study whether what is the impact of having one wall versus two wall. Is the material optimized? Uh, and you can do those studies. All right, so just to recap on the paper-based containers, so we can model paper wrinkling, so uh, we can uh, we can model the actual process of paper being transported to the machinery, the production line feeding, the paper distortion, uh, going forward from papers to the liquid cartoons. So liquid cartoons, the key challenges, we want to avoid unexpected failures. We want to ensure that it stays sealed during various transportation, processes. So I'll go into a detailed demo in this one, but just wanted to kind of highlight the, one slide which kind of encapsulated all. So if you look here, this is kind of a complex problem. You have your you have your packaging material coming off the reel, and it's being fed into your machinery. So we need to fold the material, and that folded material then needs to be cut, and also if possible if we can model the fluid that so that the interaction between the fluid and the structure can be captured. So this was actually done by Tetra Pak, and you can see this on the process on the right, where which actually being done. So as I said, this is kind of a complex problem to be able to handle so much deformation, to be able to handle the fluids as well as the solids under a single solver. So what we use is a CEL technique, or the coupled Eilerian Lagrangian technique. So that allows to model much higher deformation, and also allows to model fluids within the single solver. Obviously it depends on what's the level of physics that you want to capture in your fluids. If if you need to capture more complexity in your physics, we would need a fully coupled structural fluid structural interaction approach. So for next week, talk about the filling. So with filling, so really, what are the different workflows? We have fluid sloshing. Essentially, what we want to ensure, we want to ensure that our filled product does not end up being too thin, that it breaks during transportation, or or during drop, and we want to look at the stresses for that. We want to look at the fluid sloshing. We want to look at the predicted wrinkles and fold in it. So we'll take a deeper dive into this, onto the fluid flow here. So we'll first go over the general flow, the goals, and I think I'll directly jump into the demo here. So again, this would be kind of an end-to-end demo. So what we have, we start from the design of a flexible package. So we start from so for designing the package, we use the CATIA app. We use the generative shape design in CATIA, where we can build the geometry for the flexible pouch. And once you build the geometry, you can export the drawing file for your artwork, and this can be actually be done all within the platform, which is the beauty of it. The idea really behind the 3D experience platform is that it provides a unified database for your CAD, for your PLM, for your simulation. It kind of links everything together, so it makes the integration part seamless. And for anybody who has been a simulation analyst knows that like once you get your CAD geometry from the designer, there is often a lot of iterations back and forth, and also there is a great deal of cleaning up that you may need to do, and a great deal of work which is probably involved in just to clean up the geometry and make it ready for simulation. So really the idea behind this is that makes this the whole platform approach makes this easier. So once you have once we make the pouch, we will do the filling. But first we'll inflate the pouch with pressure, and once we have, then we would fill the pouch with liquid, and on the filled pouch we will seal it, drop test it. You can optimize it in various ways, and we can also create a cloud mesh of the final result and export the STL file. And using the STL file, we can recreate back the surfaces, or even 3D print it. We can extract back the deformed shape again for subsequent artwork. And you can actually simulate how the product would look on the shelf, how the whole end-to-end product would look on the shelf. So the whole platform kind of covers the goals both for the technical designer as well as the simulation expert. For the technical designer, for the creation and the validation of the design, artwork, labeling, material deformation, and how the product actually looks from a customer usage standpoint. And for the simulation expert, the various loading scenarios as well as incorporation of the material models. So the workflow is fully covered in the 3D experience. So the rendering is based on realistic results here. So we'll go over it so that actually will give more idea. So this is really the CAD part. So I'm going to skim over this part a little bit since the seminar is focused more on the simulation side than on the CAD side. The idea really is that you can you can sketch your pouch, you can create offset, create two surfaces, you can seam together the surfaces, you can create your sprout, and you can assemble all of that. The end of it, again, we have a video for this which will make it more clear. So you have a design of the flexible pouch, and you have those various components. You can export it, and you can export it to Adobe Illustrator for your artwork rendering. The idea really is that to emphasize the unified nature of the platform again. And now on the simulation side, we can export. Well, it's the same platform, so all you do is you switch the context. You created a CAD, you go ahead and open your simulation apps, and you can define your simulation scenarios. So first we mesh each of the surfaces with quad elements with a quad dominated mesh. We apply material properties on it, defining some density, elasticity, and we can tie the surfaces so that so essentially to simulate the seals. We can define the damage for those. Whether the seal will actually um, whether the seal will actually kind of break under stress and so forth. Just kind of to take a just to I see there is a question probably, but I'll take the question and answers at the end of the seminar. We'll have some few minutes for question and answers. So once you define your seals, you need to define contact. And what we have in Simulia, the Abacus solver, is what we know as a general contact, where basically you don't need to define where the all the all the contact definitions individually. You can define it just, automatically you can say include contact for the whole domain, and that makes it much more easier. And then we define the cavity where the fluid is to be filled, and we will inflate it initially with air. To simulate air, we can define some bulk modulus. For the air and the density, and for the sake of simulation, we define the sprout as a rigid body, and we run the simulation in explicit solver, so which is a part of the Abacus tutor solver. So the idea behind explicit is that it is able to handle higher deformation much more easily without getting into too much technical details. So it doesn't try to it basically it basically tries it doesn't try to solve the whole system of equations simultaneously. It relies on the past results, but it takes very small time increments, and that enables it to handle complex deformations much more robustly. And so so we have this process here where we inflate the cavity with air. So here we have modeled air with hydrostatic fluid elements, what we call a hydrostatic fluid cavity. So really, it's a much more simplistic way to do it rather than actually doing a full-fledged FSI technique here, because all we are really interested is in the bulk properties of the air, and this kind of allows us to handle that. So this is a displacement plot of it and a stress plot. So next we will look into the filling of the flexible package. So basically once you have it, you can also uh, I'll talk a little bit about the 3D play. So you see this word 3D play here. Really, the idea behind it is uh, the idea behind it is that the output files from finite element models, they can be huge. They can run into gigabytes and stuff. So 3D Play provides a lightweight interactive viewer which will compress your files and actually enable it to play with the model. You can integrate it. I mean, it's kind of it's a much more lightweight way to visualize things and to archive results and to view it. And it's integrated with the platform. So you can look. I mean, so basically, this is the addition of mass. You can look into the XY plot here. As as we progressed in time, the time is on the x-axis, the mass is on the y-axis. So as we progressed in time, we added mass to it, and essentially once the mass reached some stable state, the analysis was coming. You can see that it's stabilized, the simulation stabilized there, and the total mass of the cavity we can query for that, and so we know that we have kind of put in the idea. So in real world, basically, if this is just we have inflated it, we need to fill it with a liquid. So that's what we will handle next. We will fill it using spherical particle hydrodynamics material, which is a different approach. And so that's a different approach than the hydrostatic fluid elements. Hydrostatic fluid elements is more like a simplistic approach where you can model the bulk properties of the fluid, but you don't model kind of the individual details. So the SPH approach allows you to model the fluid in a little more detail. So for the filling, what we would do is that is we will have first we will fill the liquid, then we will seal the faces, and then we will finally do the drop test. So we would have liquid solid, which will be converted into spherical particle hydrodynamics, which is step A. We will have guides for the seal phase, which will be moved to seal the package. We will take the results from inflation for step A. Inflation is where we just applied the hydrostatic fluid elements to inflate the cavity. And once we have filled the liquid, we will do a drop test here. And we will define, we can, we will, and we can define the constraints using the restraints load manager here uh, within the platform here. So, uh, so for the simulation, we start with inflating the pouch and let the top open. We take the shapes from the inflated of the inflated results, and once we have created, and then we add a circular, and we add the liquid volume to the circular tube here. The liquid is being modeled as SPH particles. So, SPH allows to, well, with SPH, you do not have a mesh, you have individual particles. So, that allows you to model extreme deformation much more easily. And so, for liquid filling kind of approaches, there are a number of ways you can approach it. You can use the Eilerian approach within, well, within Abacus solver, you can use the SPH approach. We can use the fully coupled FSI approach. So they differ in terms of the computation time and the complexity of physics that you can capture. If you want to capture all the physics, you want to go with a fully coupled fluid structure and interaction approach. If you want to do it much more cheaply, then depending on what is the complexity of a problem, you can go with it. You can go with either the hydrostatic fluid or the SPH approach. SPH, I would say, is kind of a good trade-off uh, from going for the more expensive Eilerian techniques and or a fully integrated approach. So, I have a video here, so I will not spend too much time here right now. And we fill the process. We fill the pouch here, and with the uh, first we have this with liquid first inflation here, and then we have the filling process with liquid filling here. We have the SPH particles, and from the SPH particles we can smoothen those HPH particles and create a much more cohesive surface here. So once we have filled it, we apply the we apply the constraints. We apply the constraints over and seal the package, and you know, and we do the subsequent analysis. So, I mean, since we are, I mean, I realize that we might be out of time, so I'm going. I mean, I wouldn't go into the details of this each of the slides, and we do the drop analysis. So, what I'd like to show really is that we would like to go with the video here, which would kind of encapsulate everything, and I think this will, anyways, give a much better idea of the whole process. So, we create the CAD geometry here. We offset the surfaces. So this we create the sprout. I mean, and this is we are using the CATIA generative shape design app. We have our assembly. We assemble it together. We can export it for we can export the drawing and use it, and that is kind of a different use case. You can use artwork on it. You can impose your artwork on both the undeformed as well as the deformed uh, geometry. Okay, I'm sorry. I think I'll try to push this ahead a little bit. I went to the next slide. Okay, so we can export that in Adobe Illustrator. I'll skip this part of the artwork part, and then we go to the simulation piece. So we can switch context to the simulation piece and define the explicit dynamics process. For this, we can define the time for which we want to do the simulation. We mesh it, uh, give a mesh size, and we can define fairly complex meshing rules in this. Uh, and we can define the tie constraints. So we can define the seal over here. We define the region for the fluid cavity, the region that we need for the fluid cavity, and we define the sprout as a rigid body. For the sake of the simulation, for the purpose of simulation, we apply the gravity load, and we then apply the cavity pressure, and you know, essentially we are done. So really, I mean, if you know the whole process, I mean, if you are familiar with the tool, it can be the simulation in itself need not take very long. It's the validation of simulation that really takes much longer than the actual doing of simulations. So once you have the simulation, we can subsequently use this, uh, for the filling process. We can export the deformed shape. We can use, for the we do this with the SPH. So we define the restraints, we have defined the ground, we have constrained the ground, and we have defined, we basically defining the scenario, that the ceiling as well as the drop scenario. So the liquid fill here, and you can see the filling process. After the filling, we do the sealing, and you can see the simulation, the animation of the sealing process. So we move the two guide clamps to seal that, and we have uh, and then finally we do the whole thing with the drop. And and what's cool here is that you can actually export the deformed shape as an STL. You can recreate the surfaces. There is a 3D printing app here. You can actually print out your flexible package. So, I mean, you can send it to the 3D printer. You can also use artwork for it. You can do, it's all within one platform. So we added this. Okay. So we get the digitized shape out of the deform shape, and we have advanced techniques, the UV parametrization and stuff, where you can actually superimpose, you know, you can superimpose your artwork on the deformed shape directly. So I would not go into that detail. So I'll jump on to this, for the I'll not let the video complete because it deals more of the part which is not really so much the simulation focus. So the end result really, this was from simulation. This is, and like the artwork was kind of superimposed on it, and you can actually visualize how it looks in the shelf. Uh, we can also do thermoforming. I mean, just for the food plastic tray forming, we can get the thickness in thermoforming by a thermoforming analysis. So I think we are kind of close to the time, so I will really open it up for the question and answers. For any question and answers you can have, you can type your questions in the chat window, and I will try to answer it to the best I can. And if necessary, we can connect offline and and do of it. Yeah. So the one question is, would the rendering be realistic enough to use for marketing and sales? I would say absolutely. The rendering would be realistic for marketing and sales, and that's one of the goals of the platform, that it provides a complete end-to-end solution, right from your requirements, design, manufacturing, simulation manufacturing, to how the consumer would actually, how it would appear to the consumer. Uh, this was probably addressed in a previous webinar, but is it possible to model very large deformation by larger rigid polyethylene such as crash or blast? Yes, it is possible to model larger deformation of polyethylene, I mean, for PET material and polyethylene. And for crash and blast, we would need to use specialized techniques, but we can do it. We can do it uh, within the Abacus solver. So, any questions you may have? Any questions, feel free to ask. I will hang on for a few minutes here, and if if there were none, we would hang up. I mean, and feel free to ask questions even after it. I mean, even if you want to connect, just send us an email, and we will try to follow on it. All right. I think there are no more questions. So thanks again for everybody who attended. And again, as I said, feel free to shoot us uh, any question we may have, and we can take the discussion offline. And yeah, uh, one thing I'd like to mention is that there is also a cloud version available if you want to try it out. There is a cloud version of the 3D Experience platform, and that if you want to try it out, and we can also have a trial version. And uh, our email is support@viascorp.com. So, if you have questions, our email is support@viascorp.com. All right. Thanks, everyone.